So if you remember, the last time we discussed at the very end, we got at the very end the two estimates of the permeability in this case. So it's imposing in particular a gradient of, a unit gradient of pressure along the in one direction. The idea was to get the kxx and the kyx as the two components of the velocity field, of the average velocity field due to this alpha equal to E1. And obviously the same could be done considering the E2 direction. In that way we got an estimate of the permeability. We have seen an estimate from below and an estimate from above. And okay, we said that we should try to formulate the problem for a numerical integration of the equation. Okay, and so what we started from was to generate a discretization of the domain, which looks like that. So essentially, what is the main point that I wanted to point out? Okay, this is just a discretization via the software GMSH, but the main point is that we want to assign levels to the boundaries, because later, when we are going to construct the numerical solution of the problem, we want to impose different boundary conditions on the different parts of the boundary. In particular, if you remember, what we said is that we want to assign periodic boundary conditions on these two sides. So the velocity here, imagine having two components, should be the same at the corresponding point. So if this is the Vx and the Vy, this should be the same Vy, Vx. The same at the top and the bottom. So if I stay here and I have this velocity field, I should get exactly the same at the corresponding point. So these are purely periodic boundary conditions, so we are not going to prescribe values, but just periodicity property. But on the other hand, and so somehow we have to put labels to be able to recognize later these boundaries on these two sides and on these two sides. And on the other hand, on all the quarter of circles, we want to assume zero velocity. Because if you remember, the physics is that these are our grains, no? And as we are playing with a viscous flux, when you have a viscous flux, you have the condition at the interface between a wall, in this case the grain, and the fluid implies that the velocity is zero at that interface. And so this is our target. so this is what, more or less what, this is more or less the file that generated that this is the file that generated the domain that we are looking at. So we have, first of all, to assign all the points. So just here. So this is the point 1, point 3, the point 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay. This just because of the syntax of this geo file, which are the input file of GMSH software. So you have to provide them as 3D points. So then we will remove the third coordinate in the Phoenix code. And then you have to identify, so notice that you have to label each point and then each line and so on. So you have point 1, point 12, then lines, which are line and circles. So line 1 is this, circle 2 is that, line 3, 4, 5, 6, 7, and 8. With a syntax which is quite obvious, in the sense that for lines you have to provide the 2 points joining which are joined by the line. For the circles, you have to specify the starting point, for instance 2, the arrival point 4, and the center 3. So 2, 3, 4 is this circle here. Okay. And then there is so these are all parts. These are all the lines, and then the global line, which constitute the boundary of which will constitute the boundary of our domain, which is the join of all the lines. Okay, so curve loop 9 is just the curve grouping. Grouping all the curves. Then, as I was telling you, this condition is just specified in order to guarantee that the further discretization that we are going to introduce later is respectful of periodicity, in the sense that we want to generate a discretization such that the same number of nodes are placed on the left, for instance, and on the right side, and the same from the bottom and the top. Because obviously we want to impose periodicity conditions, but if the discretization is such that here you have not the same number of nodes as there, you are breaking just because of your discretization procedure the periodicity that you want to impose. Okay. Then you have to specify what is the domain, in fact, which is a surface. So you see that you have we had fixed 12 points, 9 curves. This is just a condition. One surface, plane surface 1, which is equal in fact, this means that when you specify the plane surface, here you are indicating what are the boundaries of this surface. In this case, the boundary of the surface is just the internal part of this domain, so plane surface 1 is just the domain bounded by curve 9. This is the meaning of this statement. Okay. We will see how to prescribe a domain with an hole, which is technically similar, but in that case we should indicate both boundaries. Then, so this is pure, until this point, this is purely geometric assignment. Then you have, as I was mentioning before, specify what will be the physical domain and what will be the physical boundary. So essentially this part of this script indicates what is the domain within which we are going to solve the problem, and what are the parts of the boundary that we want to clearly indicate. So you see that the physical surface, so the physical domain, let's say, is 1, and it is obvious because we have just this. On the other hand, we are listing a certain number of physical curves where we are going to specify boundary conditions. So these were the labels from 1 to 8, the labels of the different curves that we generated. But now we are specifying these physical curves, which are really the part that we are specifying the labels to be used later in the code to specify boundary conditions. So this is the curve 1. I'm saying that physical curve 1 is the line 7. Physical curve 2 is the line 3. Physical curve 3 is the line 5. And physical curve 4 is the line 1. And then there is a physical curve physical curve 5, which is what remains. So this 5 is in fact the join of all the parts describing the boundary of the grains. Why? So this is the union of these 4 parts, because on these 4 parts we are going to specify the same boundary condition, which is 0 velocity. Okay. Then this is probably not necessary. So we can skip. And the last instruction is just grouping all the curves and specifying how many subdivisions you want to fix for every part of the boundary. And this is related to the mesh that we are generating. And so this generates this file. So once you have written that script, you see that here we are just opening the same document. You see that it is exactly the square extruded by circle geo, and this is square extruded by circle. So it's the same file, exactly the same file, just opened within the GNSH software. Okay. So once we have done that, The point is that here, in fact, the GMSH file does not generate the mesh. Then here, when I open the file and you see that you have several options, and among them the mesh option, you click here with 2D, and you generate the mesh file, and then you save it. So saving, it generates the file. Yes, this one. No, sorry. Yes, this one. So this MSH file is the file including the mesh that we have generated. Okay, so this is our starting point. The point is that typically when you use a finite element software, a finite element code, okay, the most part of the finite element codes and also the Phoenix code has its own way to generate a domain and to generate the mesh within the domain. But typically, this is for very simple shapes. If you need to generate a more complex domain, it's better to refer to a specific software which is designed for this special target. In this case, we probably could also use directly the internal the part of the software, the part of the Phoenix code which is devoted to generate meshes, but it's not a bad idea to use this kind of parallel scripts. In any case, it's very simple, so it's not it's even simpler to generate the mesh like that than directly inside the software. Then the problem is how to incorporate. So you should be careful in using this kind of softwares, because you have to check before if they are supported, the files that are generated are supported or not by the Phoenix code. Okay. So now, we can move into our Phoenix code. So the Phoenix code is this. So you have, I think that you have seen partly with Laurent, or you are going to do something about this Phoenix implementation. Honestly, I will give you some information, but we are not going to enter in all the details of the script. If you have questions, obviously we can discuss. But the main idea is to give you the flux of information. Okay. So essentially, here you are importing a certain number of functions that you have to use. This is Phoenix X, and so it uses Dolphin X and Basics X. So this. So the main point for the moment is that you have to import GMSH, because we need to use functions able to manipulate the file that we have generated within GMSH. And if I remember well, also this is important. I try to minimize as much as possible the requirements. It is possible that I didn't eliminate all the non-strictly necessary import, but I think that these two are both important. Then we will come back on the others later. So first of all, what you need to do is to manipulate this MSH file that we have generated. So the mesh file. Why? Because okay, MSH designates can be manipulated by Phoenix, but not directly. So it should be treated somehow. So you see that here, so till this line, you are just importing a certain number of functions. Okay, so the very first instruction is this one. So here you see that you use this mesh IO, which has been imported at the beginning, and it is used to read the file that we have generated from by GMSH. So the square extruded bicycle MSH was the file of the mesh. Okay, and we call this mesh compile. This is just the name that we are attributing to the file. Okay, so this is just let me see. So essentially here you have to create, because this one is a mesh file, but it's not directly exploited cannot be directly exploited by Phoenix. Okay? So the point is that you need to extract from this file a certain number of information that then can be used in the code. In particular, what is the point? The point is that you need to you have your discretization, so and each element has its own label. Because it must be possible to identify the different elements, and also so you need a way to identify every element, and also you need a way to identify every facets, which are the boundary of the element, which correspond to the contact lines between two contiguous elements. So the point is now to extract from this MSH file information relative to elements and phases. So elements, it's obvious what we are thinking of. Facets are just the boundaries of every element, which also identify the contact, the lines through which the couple of elements are in contact. And this is in particular important when we want to specify boundary conditions, because we need to specify boundary conditions on the nodes which are on the facets staying on the boundary. So this is a little bit tricky, but this is clear. Okay, so so in fact this function I'm not entering in this. Essentially, it takes the file that we have imported from GMSH, the MSH file, and it manipulated in order to generate files that can indeed be used by Phoenix. And so you see that this create mesh this is a function. When you find this in Phoenix, means this is a definition of a function that operates a certain number of assignments. In particular, here it is also going to eliminate the last coordinate of points. But you see that you apply this function, this create mesh, both to generate line mesh and triangle mesh. So this means that line mesh is used to is introduced in order to identify facets, and triangle mesh is introduced to identify elements which are triangular elements. Okay. So essentially, it is this indication line and triangle that tells you what kind of information should be extracted from this file, which is the one coming from GMSH. Okay. And once you have generated this line mesh or this triangle mesh file, then you save into this format XDMF file for facets and for mesh that can be exploited by Phoenix. So this is, let's say, a kind of starting procedure to import into the code the information coming from the MSH file. And so this is the last step, because we are finally reading these files and defining these two quantities, mesh equal to something and ft equal to something. So we are defining what is later exploited in the code as the mesh and as the facets of the associated to the mesh. So the list of elements and the list of facets of our discretization. This seems trivial. I mean, from the point of view of let's say, of understanding, it's we are not adding a significant added value to this what we were just describing at the very beginning, but it is fundamental. These are fundamental steps in order to later introduce manipulations. So this first part of the code is just devoted to correctly import into the code the information coming from the geo file and the MSH file later. Now, here, just to be sure, this is a check that I did. Just to be sure that the code was correctly reading the information coming from the MSH file, and then via this manipulation storing correctly data in this mesh and this FT. What I did was to calculate the length of each part of each part of the boundary. So this measure, this is a function which is imported. You see it is it is indicated here. Yeah, here. UFL is the library from where a certain number of operation as you see divergence, gradient, inner product, the volume element and measure are important. And so what I'm doing here is just to calculate over the domain mesh, which is defined over there, and over the subdomain Ft, which is the subdomain of the facets, to calculate essentially the measure of the arc labeled as 1. 1 was what? 1 was this. So I should expect that from this length element 1, it should provide me the basic information to calculate this length. In fact, the final calculation is here. This is just the element, so this is what I called here ds. So this is the elementary length over there, and the same for the other subdomains, so 2, 3, 4, and also 5. And then this is for the moment just I mean, I just comment on that because I tested and then it was not necessary. So I eliminate. So here I'm just assembling for using a scalar field this finite element form 1 times the length. So what I'm doing here, I'm just saying, okay, I have defined the ds relative to the element 1, the ds element relative to part 2, 3, 4, and 5, and then I'm calculating the integral. When you see this FEM form and then assembly, this means that you are constructing the form which is this one, is 1 ds, 1 length element 1 times the element 1. So essentially it is ds, ds1 if you want, and then when I'm doing this assembly means that you are evaluating the integral over the parts of the boundary which have this label 1. Okay. The fact that we introduced the labels in the geo file is indeed read at this level. Okay, and so from here, as this is a 1 by 1 cell, this is at the origin is one cell 1 by 1, and the radius was 0.25. Okay, so in the end, the result of this length should be 0.5. So this is something that you can check just to verify that. To verify that the file is correctly reading the information coming from the MSH file. No? And so this has been done for the 4 subdomains 1, 2, 3, and 4, and also for the 5th part, which is constituted by this 4th of circles. And so in the end, what you should recover from this length element 5, and in particular from this FEM assembly scalar of FEM form 1 times the length element 5 is the length of a circumference of radius 0.25. Okay, and in fact this I checked, and it works. Okay. So this is and the same you can do for the volume. So you can calculate just to the volume, the area, obviously. So the instruction is the same, but in this case, instead of using the ds defined like that, you directly use the dx, UFL dx, okay, defined over the domain mesh. So you are doing the same calculation, but this was done on, for instance, on the line 1, and this calculation here is the integral over the area of 1 dx, where the area is the whole domain. Okay, so the domain is equal to the mesh, and then in such a way that you can verify that the volume is correctly calculated, because the volume of this, it is easy to know. It is 1 minus the area of the circle of radius 0.25. So you can have just a quick check of what you are doing. Okay, so this is just these are just preliminary steps to correctly import the mesh, and to verify that everything is working correctly. So we checked a couple of things that are important. So first of all, okay, that the file MSH is correctly read and correctly translated into these XDMF files that in fact you have here. Once you run this, you see this script, you see that you generate these two files, and mesh XDMF and phased mesh XDMF, which are these ones. Okay. Phased mesh XDMF and mesh XDMF. So what I was telling you is, this is first of all we have checked that these files are correctly generated, but most important, we have checked that we are able to read the labels that we put in the file. Okay, so these labels are not introduced at the level of the Python script that we provide the solution of the program. These are just read from the MSH file generated via the GMSH script. Okay. So, but this is, let's say, purely geometrical information and some let's say labeling of the domain. Now you know that in order to generate solution via finite element, what you have to decide, what you have to adopt. You have to adopt a suitable kind of element. No? In fact, the point, if you, for sure you remember, at least I hope so, when you play with finite elements, what you are doing, what you are assuming is that your domain, the I mean, you have a weak form, let's say this. Huh? You start from a suitable strong form. We are going to come back on that in a while. You start from a certain strong form of your differential problem, that in our case is the Stokes problem. We have seen this. Then you go into a weak form. And the weak form is written as the integral over the domain of, for instance, in our case, there will be for sure, among the other terms, there will be for sure a term like that, no? dv by dvi by dxj, dui by dxj, where the u, for instance, is the solution, and the v is what? Is the test function. Okay, we are going to rewrite once again this, and then other terms. But in finite elements, what you do? You introduce a discretization of your domain. So instead of working with this integral, you work with a summation over a certain number of elements of integral over dE. So you split the domain into subdomains, and this is the first part of the story. But the second part, and most important part of the story, is that you look for special kind of solution. So you look for solutions which are combinations of suitable shape functions. No? So you choose what are the functions you are going to project on the solution and the test function, and you represent, for instance, the UI over the domain dE. You represent it as a summation of AI ij, summation over j. So what is the idea? The idea is, for instance, in the 1D problem, is that you have this element with node I and j, and you represent your function, for instance, as a linear combination of these two shape functions. This is the simplest choice that we can imagine, considering linear elements. So you have a function which is 1 in I and 0 in j, and the other one which is 1 in j and 0 in 1. You can complexify things introducing nonlinear shape functions, but this is the main idea. So on every element you have a linear combination. You have that your solution, so for instance your u is a1 f1 plus a2 f2. So the f1 and the f2 are given functions, and your target is just to identify the weights. So this is what you are typically doing in finite elements. So you assign an approximate form of the solution as a linear combination of suitable shape functions defined on every element, and you reduce your problem to finding the coefficients of the linear combination of these functions. Is it clear this in your mind or no? So the starting point when you work with finite elements, and in particular with finite element implementation, is to choose what kind of shape function you are going to manipulate. And so this is what is written here. So now what is the point? We have to come back to our problem to understand what we are going to do. So remember that our problem is the Stokes problem. So if you remember the strong form of the problem, this was the Laplacian of Vi minus the gradient of P equals 0, with the mu here, the viscosity. Then the Vi comma I equals 0, and the so this on in the domain, so in D, let's call it D. Then V equals 0 on the what we call ISF, which in our formulation ISF coincides with the part of the boundary labeled as 5. No, this is what we said. And then V periodic on the rest on the residual part of the boundary. No? So V periodic. Sorry, we call it omega F. V periodic on the boundary of omega F minus ISF, which is exactly what we said, requiring periodicity between 1 and 2 and between 3 and 4. Okay, so this was our strong formulation. So, and if you remember, what we did was to split this gradient of pressure into two contributions, because we said that P could be written as a P, as a P. So here we are introducing zeta coordinates. So zeta 1, zeta 2, and zeta 3 are the three spatial coordinates in general. In particular, in this case, the zeta 3 will be always 0. So we wrote this P, if you remember, as alpha j zeta j plus phi of z, in such a way that to split the two contributions to P, the periodic one phi and the linear one associated to alpha, which was which is the macroscopic gradient of pressure. So in the end, this means that this problem can be written like that. This gradient of P just reads as gradient of phi, and here we put an alpha I. Okay. Is it fine for you or not? We have said this plenty of times. No? Okay, so pay attention that here I is because the V is a vector, so Vi is the I component of the vector, so this is the Laplacian of the I component of the velocity. This is so this should be written like that. This is the I derivative of phi, and this is the I component of alpha. So writing this the problem in this form means that our unknowns are the phi and the Vi. So we have 4, let's say 3, because for the third component of the velocity will be 0 because we are in a 2D problem. So 3 unknowns, V1, V2, and phi, and a loading, which is this alpha. And in particular, what we are going to do is to discuss separately the case where alpha 1 is alpha 1 is the vector 1, 0, or alpha 2. So the first problem that we are going to solve will be this, and the second one will be vector. Because our target is to calculate the solution in terms of velocity in particular, and to get the average of this velocity over the cell in order to obtain the permeability. We said plenty of times. But keep in mind that our problem is defined in terms, not only in terms of velocity, but also in terms of pressure. If you remember, the formulation that we adopted in the analysis that we carried out till last time, and that allowed us to get the estimates, were based on the hypothesis that the space where we were looking for the solution V and the space where we are defining the test function relative to the velocity problem were special kind of spaces such that the divergence of the function staying in those spaces was zero. So in fact, when we discussed the the solution of the problem via variational formulation. What is it? Yes, it is here. No? We said we consider test function U and also solutions V such that the sufficiently smooth, okay, having a vanishing divergence. So we look for solutions and test function within this space. Or here we are not going to do this. So we are going to look for a solution of the problem in a space for solutions for functions V and test functions having not this additional condition to verify. And so this means that in the end we are obliged not to look for the solution just in terms of V, but also in terms of phi. If you remember this hypothesis of playing with a set of trial and test functions staying in this space allowed us to eliminate every contribution related to pressure, which in this case is phi. So the final problem, the final weak form, was just involving velocity as the unknown of the problem and test function U as the quantity to be used to weight velocity unknowns. But pressure just disappeared from the formulation because of this assumption of looking for the solution into this constrained space. So now the point is that from the theoretical point of view, it is nice to play with this kind of space. From the numerical point of view, it's less obvious. So it's easier to not put constraint on the space, because constraining the space, this means that you have to choose in a suitable way the functions, elements of this space. And this is not so obvious. So it's simpler to not assume this restriction, but obviously we have to pay something because now the weak formulation will be, I'm going to rewrite it, the complete weak formulation is not going to involve just the velocity, but also this phi. And so we have to state something on the space where we are looking for the solution of the problem, not only in terms of V, but also in terms of phi. So if you remember what we did here, I'm not going to redo all the calculation, but I will give you the weak form that we have to manipulate. But the first point is that as we have our unknowns are Vi and phi, I, let's say, equal 1 and 2, we are in 2D. We have three unknowns, and so we have to specify finite elements for the two unknowns, and this is exactly what is done here. So you see that we we specify P1 and P2 as Lagrange elements for essentially these are at this level, these are just two kinds of Lagrange elements. Lagrange elements means polynomial elements. Okay. So polynomial elements of degree 1, and this is indicated here. And so till now, so till the first three assumptions, three information, you see that it's exactly the same. So Lagrange elements where on mesh cell topology, cell name, blah blah. So this means just that we are taking from, attributing this element to the ones associated to the mesh. So we are constructing on triangular elements. So when in 1D, these are the shape function that I was showing you before. In 2D, if you have the analogous of that is that you have triangular elements, and your functions are defined like that. If you have node I, j, and k, you have a function that is let me find a way to do better. So the element is this I, j, k, and this is, for instance, the shape function relative to node I, which is 1 at node I and 0 at node j and k. This is a linear, in this case it was a straight line, the generic shape function, and this in this case is just a plane. So these are both linear functions, but obviously this in 1D and this in 2D. Obviously for the other nodes it would be similar. For this one it would be something like that. The function, and for the third one similar. Okay. So here what we are saying is that we want to take Lagrangian elements, so polynomial elements, over the mesh which has been imported from GNSH. One is the order of the polynomial, so Lagrange polynomial of order 1 means linear. And there is the, so for this moment this is the same, but P2 and P1 are introduced separately with this indication here, because we need to specify Lagrange elements for the vector field V and for the scalar field phi. So finite elements for V should be of vectorial kind. So P2 are Lagrangian elements of vectorial kind, and this shape equal to means that the dimension that we are looking at is because we are in 2D and we are considering a vector field. And here we don't specify anything, which means that it is a scalar. So P2 is the space where we define Lagrange finite elements for velocity, and P1 for pressure. For phi, the periodic part of the pressure. Okay. Uh, then, so the so we have to define in the end what we have here is the definition of what is called a mixed element function space, which is constituted by this kind of polynomials P2 and P1. P2 for the velocity, P1 for the pressure, and the space W is the function space which is attached to the mesh and based on this kind of polynomials. So this W is the space of functions where we are looking for the solution of the problem in terms of a kind of Cartesian product between the space for velocity and the space for pressure. And so this is the way in which, starting from this general definition, we isolate the V and the Q. Don't care too much to this one, V to Q and V to W and Q to W. So V and Q are essentially the parts of this space W relative to the velocity and relative to the pressure. So we have defined, first of all, the elements that are needed for velocity and pressure. Then we have constructed this mixed element for the list of unknowns, which are V1, V2, and Phi, and then the space W where we look for the solution. And then we decompose this W into P and Q, say this the subspace of W relative to velocity, the subspace of W relative to pressure solution. Okay? So this W sub 0 and W sub 1, notice that in Phoenix, when you put a 0, for instance, sub 0, but also x 0 means the first component, and sub 1 means the second component. Okay, so it uses 0 for the first component, 1 for the second component, 2 for the third component, and so it's not so straightforward, but it's like that. Don't ask me why, but it's like that. Okay, so this part is once again just preparatory to the solution of the problem, but it is fundamental because you are choosing what kind of elements to use for solving the problem. Okay. So in this way we have stated where we are going to look for the solution of the problem. Then we will see that this is not yet the last step because we should tell to the code, so these are just the space we are going to manipulate. Then we have to specify where what is the space relative to V, what is the space relative to the corresponding test function, and the same for the pressure, but this we will see. Okay. Now the point is that so now we enter more in the definition of the problem. So we have to specify first of all the boundary conditions, then the weak formulation, and finally the boundary condition, which means the boundary conditions, the periodic boundary condition, and the boundary condition over the 5 region, the region 5, the part of the boundary which corresponds to the interface between the solid and the fluid, and then the weak form to integrate. So here the idea is that yes, so essentially this I did in two different ways. In fact, it is not necessary. this part could be, you could put a comment with that. Obviously, wherever you find this check, this means that these are just text, these are comments. So what we can do is to assign in a different way, to identify in a different way this region 5, these arcs of circle, which are the part of the boundary where we prescribe zero velocity. So one way to do that is line 95, which exploits just the level that we introduced in the GMSH5. Because you see here you are using this instruction, locate DOF topological, which has been imported at the beginning. Locate DOF topological, and later we are going to use locate DOF geometrical. So this topological location refers to the labels that we have introduced in the GMSH5. So if you remember, we labeled with 5 this part of the boundary. So essentially I'm saying call interface degree of freedoms, those relative to velocity, and this is because I'm referring to the space V, which is the space of velocity. Having a dimension which is the dimension of the mesh -1, so in our case 1, because they are on the boundary, we are on the boundary of the domain, and where I have to look for this degree of freedom. Here, Ft is the subdomain of the facets that we have defined before, if you remember. Here, Ft was the reading of the facet mesh XDMF. 5. So you are looking for the degree of freedom attached to nodes which belong to the part of the boundary labeled as 5. So essentially this instruction gives you back the degree of freedom associated to the nodes belonging to this part of the boundary, which we have labeled as 5. Okay. So this, and that. So it's a list of nodes with the corresponding degree of freedom relative to the space V. And so in this way, we have identified the degree of freedom for the velocity for which we want to assign 0 boundary condition. So this would be sufficient to assign 0 velocity. So consider this line 95. Then there is this line 101, which just introduce a vector of zeros, essentially, because we want to assign 0 velocity. So NP is NumPy library. So this assign a vector of zeros, introduce an object which is a vector of zeros, and here line 103, BC note are the Dirichlet boundary condition where on the interface degree of freedom, which we have identified before, no slip, which is this condition of 0 velocity, on the space V. So this is the way of prescribing 0 Dirichlet boundary conditions on the domain labeled as 5. Okay. So obviously there is certain number of syntax that one should learn, but the meaning is reasonably clear in the sense that you have to specify what are the degree of freedom involved, in these Dirichlet boundary conditions, to what space you are referring to, the velocity, and what is the prescription. This no slip is just a vector of zeros. Okay. So you are saying on all these points v equals 0, or if you prefer, v1 equals 0 and v2 equals 0. Okay? This is what we are saying. Another way, so this is just using the information coming from the file that we have imported. Another way to do that is using this locate DOF geometrical function that we have also imported. So in this case, you do not refer to the label, because here we are using this find function, which looks for the level 5 in this case. Here we, on the other hand, we just locate the degree of freedoms geometrically with a restriction. The restriction is introduced via this function. So, what is this? This boundary interface function. This is a function taking a vector x and a center. So essentially, it is a function that specifies that checks if a point belongs or not to a circumference of a certain center. So the idea is this, that you enter with the coordinate of a point and the coordinate of a center. You define r as the square root of x0 minus xc0 square plus x1 minus xc1 square. So we are just using the standard definition of the radius of a circumference, like written like that, where the x in Phoenix is x0, this is xc0, and this is x1, and this is xc1. So I define r like that, and then I check if this r is closer, in the sense that there is an internal tolerance. I think that I put this tolerance, but then I didn't use it, so I'm using the internal tolerance. I don't remember what is the value. Just to check that the r that I'm evaluating is equal, let's say, to 0.25. So only the points staying on, for instance, this circle verify that condition. So if I give to this function the coordinate of this point and the coordinate of this center, what I'm testing is that this point, this length is equal to r, the radius of the circle. Okay. So you see that here I'm introducing interface degree of freedom 1, 2, 3, and 4 for the different subpart of the domain that we have labeled as 5 before, and so taking once again the space V, and this means that I'm testing a function. Lambda is a generic function taking x and providing me the answer to boundary interface x00 or x10, x11, x01, which means that I'm testing if the point x belongs to this circle having center in 00, this circle having center in 1, 0, this circle having center in 1, 1, this circle having center in 0, 1. Okay? So, essentially from these four assignment, I identify in a different way the points staying on these parts of the boundary. In this way, it was what Phoenix called a topological identification, so just based on levels, and here, on the other hand, geometrical, because you are introducing a restriction via this function. Okay? But in the end, the instruction would have been the same. So you see that this is commented, but it is the analogous of that. BC naught would have been the Dirichlet boundary condition of no slip kind, so the same kind of assignment, on interface DOFs 1V, then the same for DOFs 2, DOFs 3, and DOFs 4. So either the first or the second, these are equivalent assignments. Okay, so we are specifying 0 Dirichlet boundary condition on the fifth part of the boundary. Oh, so now the point is periodic boundary conditions. So periodic boundary conditions, in fact, it's not trivial at all. In fact, we are exploiting a library, a subroutine, which has been explicitly written for this purpose, but which necessitate essentially the definition of a master and a slave region for periodicity. So essentially what we are going to say is that whatever happens, for instance, whatever happens here on this part of the boundary, the same would be there. This is the periodicity condition. Whatever happens here in terms of unknowns, clear, whatever happens here, the same would happen there. So we have to identify this correspondence between a boundary, a part of the boundary, and another part of the boundary, in particular right to left, and the same here, top to bottom. So obviously this is strictly related to the geometry of your domain. You cannot construct a completely general formulation. So, okay, this is not so fundamental, I mean, it's important, but it's just in the length, probably this I should put before, but it doesn't really. So here, in order to define this this I think it's useless. On top, left, right, and that's it. So let's stay with this first. So essentially here what I'm doing is to introduce these vectors A1 and A2. So this is just looks complicated, but it's a stupid thing. It's a stupid thing in the sense that you identify these corners, which are the four corners of the square. Thinking this as a square. So this, and skip the last component, which is the zeta component, which is always 0. So the corners are 0, 0, L0, LL, and 0L. L being 1, and I define the A1 and A2, which are the two vectors. This one is A1, and this one is A2. So if you see, A1 is what? Is corners 1, so means take of this array of arrays, the first array, so this one. Sorry, 1 is this, because it's 0, 1, 2, and 3. So with the usual, so this is the 0 component, this is the 1 component, this is the 2 component, and this is the 3 component. So A1 is corner 1, so take this and all the elements, so take this vector L0, 0, L0, sorry, yes, 0, 0, because it's the 0 component, minus corner 0. So I'm taking the difference between this point and that point, which is obviously that vector, no? Because it's the difference between this point here and that point there. No? A1 is the vector, this corners 1 takes just this vector minus that vector, which gives you trivially a vector L0, 0, which is this one. And similarly, A2 is corner 3 minus corner 0, so you take this minus that, which provides you this vector there. Okay. So now, once you have this definition of A1 and A2, which in fact can be directly stated as A1 L0, 0 and A2 as 0 L0, it's exactly the same. We introduce this periodic relation left-right and periodic relation bottom-top. What are doing these functions? So they take a vector x and just they test they provide the corresponding so let's say they take a master point and they provide the corresponding slave point. What does it mean? This left, right, for instance, you see that you start, the target is this out x. So you take a vector x as entry information. You initialize to 0 this out x. Num p zeros means a vector of zeros of the shape of x. So if x is a 2D vector, they construct a vector of 0 of dimension 2 or dimension 3 as it depends on the case. And then you say that as this is left right, you take output x0, which is x0 minus a1 0, and output x1, which is x1 minus a1 1, and return this output. So you are assigning the slave coordinates starting from a master one. So imagine that you have a point here that is your x. So your output x, out x, is what? You are taking, for output x, you are taking the x0 components of this, so the horizontal components, so it is x, it is x0 minus the first component of a1. A1, I remember you, is L0, and A2 is 0L. So output x is x0 minus L, the 0 component of A1. So you are taking this and getting that. So this is 0. And out x1, x1 minus what? Minus a11, but a11 is 0. And so, and in fact, this point has different x coordinate, but the same y coordinate. No? So we got from this point, that point, having a shift in the x coordinate of L and the same y coordinate. Okay? So this is the way in which a point on this boundary is reconducted to a point over that boundary, because we want to guarantee this correspondence between region 3 and region 2, we should know this level, and region 1, and the same we are going to do between region 3 and region 4. So this periodic relation bottom top is exactly the same, but with A2. No? So here we took an element, a node here, and the output x will be what? Will be x naught minus A2 naught, so the first component of x naught, the x component of x, minus the x component of A2, which is 0, so the x component remains the same, while the y component will shift back of L, because we have x1 minus A21. Okay? So this is just the way to establish a correspondence between what happens to the right and what should happen to the left, what happens to the top and what should happen to the bottom. Okay, so this don't care, I think it's completely useless. And then, and so this is finally, this is just, I mean, one should just look at the subroutine, how does it work? So I'm not entering in the way the subroutine work has been implemented. Essentially, in order to create periodic boundary conditions, you have to play with this MPC library, which is a multi-point constraint library, which we have to define, which we have to use, sorry, for velocity and for pressure. So I'm defining this MPCV and this MPCQ to specify periodic boundary conditions on velocity and pressure. And so you see that what I'm doing is to create a periodic constraint topological on the base of what? On the base of this periodic relation left-right that we have defined before, applied to what? To points belonging to the part of the boundary having a label 2. So I'm specifying that you, starting from points staying in the part of the boundary labeled with 2, you associate to these points in terms of velocity the same value here and there, because I'm using this periodic relation left-right. And I also to specify what are the other boundary conditions given for velocity. So this is just the way in which the subroutine has been created. It doesn't want only periodic boundary condition, but it wants essentially to know what is the full set of boundary condition for, in this case, the velocity. So I have this MPCV relative to points staying on the boundary with label 2, and I have the same for points staying on the part of the boundary with label 3, but using now the periodic relation bottom top, the other one. Okay? So essentially this part of the, so from line 142 to line 149, which concludes MPC definalize, prescribe the periodic boundary condition for the velocity field. And the same way, exactly the same way, you do for the pressure. So you have just to switch from the the V space, the space for the velocity, into the Q space, the space for the pressure, but the conditions are the same. So we require periodicity for velocity and for pressure. So once again, master points are those on part of the boundary level as 2 and S3, and the slave, the corresponding slave are 1 and 4. So this part finalize periodic boundary condition assignment for velocity, and this part for pressure. Notice that, as I was telling you before, we this subroutine wants also the other looks also for the other boundary condition assigned for the assigned to the unknown of the problem. So for the velocity we have the VC naught, which were the Dirichlet boundary condition assigned on the part of the domain level with the 5. For pressure we have nothing, and so we have this empty bracket. Okay. So the boundary conditions that are specified here are within a bracket. So I just put an empty bracket because he looks for something there, but it's just empty. So there are no specific additional boundary conditions for pressure. Okay. Okay, so now we can come back to the assignment of trial functions. Trial function means functions that should be used to find the solution of the problem, and test functions.